Okay, friends, in this intro video, we're going to look at what I would call how integrals are constructed and sort of the motivation behind them. So one of the more useful notations in mathematics is this sigma or summation notation. And this is just the idea of taking a bunch of things that have the same mathematical structure and adding them all together. So this figure at the right kind of gives you an idea of what summation or sigma notation is and what it means. And those of you who have had AP Stat or Prob and Stat before, you probably remember seeing this big scary E-looking thing as our sigma. And then we have an index here on our argument. Our argument is going to be the item that you need to be adding together. And K usually goes from 1 all the way up to some number n, from a lower limit to an upper limit, where to begin, where to stop. And basically what this says is, hey, if you're subbing up a whole bunch of a's, different a values from 1 to n, well then take each one of them individually and add them all together. Okay, so the idea behind summation or sigma notation, while it looks a little scary, isn't terribly difficult. Let's take a quick example here. So if I go from 1 to 4 on my index, and I want to take 3 times x sub I, where x is just going to be whatever number we throw in here, for example, then what we're looking at doing is taking 3 times whatever number we throw in from 1 to 4 and then subtract 1. So the first term is going to be 3 times 1 minus 1. And the second term will be 3 times 2 minus 1. And then 3 times 3 minus 1. And then 3 times 4 minus 1. And then we're going to evaluate each one of those individually and then finally add them all together to get a grand total of 26. So you can test that for yourself and see how it works, but again, it's not really all that challenging to do. I mean, you get 2 here, you get 5 here, you get 8 here, and then you get 11 here. And then when you add all of those up, you end up getting 26 as your final answer. Okay, so I want you to think about what we did in the previous lesson. Effectively, what we did was we took a whole bunch of things that had the same mathematical structure and added them together. And those things that we added together were very simply the areas of rectangles. That's what we added together. So what we're going to do is we're going to kind of transition from this idea of adding a bunch of rectangles together into this sigma notation. So let's see if we can kind of build it here for just a moment. We're going to call the width of the rectangle at the bottom delta x or delta xi. Now, I want to be specific here and say that if we cut our interval into the same uniform width of rectangles, then delta xi is going to be the same thing for each and every single one of those rectangles. It's going to be the same width, and then maybe you can use a sneakier way to evaluate the entire summation here, okay, like the distributive property. Okay, and now I'm going to say that f of x sub I, that's going to be our height of our rectangle, and it appears that we're using the RRAM method. And I'm going to leave it to you to see if you can figure out how can you tell we're using the RRAM method to get the area under this curve. See if you can look at the graph and figure it out. I'm sure you probably already have just by looking at the graph here. Okay, so there are 4 rectangles here, from I going from 1, 2, 3 to 4, and we're going to find the area of each one and add them all up, and this is the sigma notation that we're going to use. It's the height of the rectangle times the width for rectangle 1, and then the height of the rectangle times the width for area 2, the height of the rectangle times the width for area 3, the height of the rectangle times the width for area 4. Add them all together, and this is what you get. All right, so right now this seems like an overly complicated and mathy way of doing something that is pretty simple to understand. So when we wandered through the lesson of the different RAMs, the MRAM, RRAM, LRAM, we know that it's not hard mathematics to do, but it is kind of tedious because you're doing the same thing over and over again, and it just feels like you're caught in an infinite loop until you're done. Okay, But effectively what we've created is we've created what's called a Riemann sum. Okay? And a Riemann sum is named after the German mathematician Bernhard Riemann, Georg Friedrich Bernhard Riemann to be specific. And you notice he only lived for 40 years. Wow, talk about accomplishing a lot in a short lifetime. If we take a Riemann sum and generalize it for any number of rectangles, call them n rectangles, then we get this. We go from 1 to n, and then you're going to take the value of the function. Now, obviously, we need to be a little bit cautious here about how we define our endpoints of each subinterval, or maybe we call this the midpoint of each subinterval. Somehow, some way, we're going to have to call attention to that just to make sure we're on the careful side here. And then, so this is the height of our rectangle, and that's the width, and n is the number of rectangles. So we could have, 4, we could have 8, we could have 200, we could have however many we wanted. And this is going to be what's called a Riemann sum. So that's sort of where the motivation gets for our different RAM methods. So what I want to do is I want to take the limit of this sum as n gets really, really, really large. Okay, now here's the catch here. N is the number of rectangles, and I want that to get as big as possible. So I want this number right here to be as big as humanly possible. Now remember what a limit is. A limit is as we approach a certain value for our variable. What is the value approaching for our function itself? So here's what the deal is. If we have this situation where we've got some function f of x, and we go from 1 or just, a to b, or I guess, I don't know, however you want to phrase it here, however you want to call this. Let's call this a to b, actually. Okay? And what I'm interested in is from a to b is I'm interested in this area right here. Okay? As I create more and more rectangles, I am making them progressively razor thin. And then as I make these razor thin, they are going to add up to something and approach something that is going to be the correct area underneath this curve. Okay? So what we're going to do is call this a definite integral of a continuous function on a to b. So if I wanted to find out the area underneath this curve, I'm taking what's called the definite integral. The definite integral is really the limit of all these Riemann sums that we can do for however many rectangles we want, and we want that number to be as large as possible because, as we said in lesson 6a, we want this to be as accurate as we possibly can. So in short, take the region with an area under a curve, break it up into razor-thin rectangles, find the area of each of those, add all of them up, and voila! You have the area under the curve. Okay, now again, this sounds like it's a really, really challenging thing to do mathematically just from the standpoint of you've got a lot to accomplish here. So I would say to you that coming soon to a math class near you is going to be a much more efficient, effective, and accurate way of pulling off what's called a definite integral. And when you see what it is, you're probably going to go, whoa, that's cool. I know I sure did when I was a student. So that's what I've got for now, folks, on our little intro here. And I hope this kind of sets the stage for what we're going to do coming down the road. Now, in the rest of this lesson, we are going to do definite integrals for sure. But we're going to do them in such a way that we can find the area easily. And that's going to be shapes that we already know. So that's kind of a little preview. That's all I got for now, folks. Enjoy, and we'll see you in class.